Automated Acoustic Species Identification.
Hey everyone, my name is Juan Dominguez.
Hi, I am Yuying Fan.
And I'm Daniel Sarafia. Non-invasive biodiversity monitoring, where we have a bunch of different animal species and we want to study them without disturbing them. There are multiple ways to achieve this. Currently, we have camera trap technology planted throughout many of Earth's ecosystems. As seen in the video, this is great for tracking larger animals that tend to stay quiet, and as a plus, camera traps generally have a small footprint. However, they also have some shortcomings. This is why researchers want to explore acoustic monitoring as a way to fill in these gaps. With acoustic monitoring technology, we can achieve a 360-degree field of hearing as well as the ability to detect smaller life forms such as insects, birds, and rodents that may not clearly appear in photographs. One great way to deploy this technology is with a cheap, small, and lightweight recording device called the AudioMoth. With about 100 units deployed in the Peruvian Amazon, this product gets a steady flow of audio data to analyze and process.
But all this audio data can easily pile up. With 4.5 terabytes or equivalently over 1.7 thousand hours of audio, how can we extract interesting sounds without too much human efforts? The answer is machine learning, the best friend when it comes to large datasets. In this project, we start from bird vocalization detection by training a recurrent neural network model. When you feed a clip to the model, it returns its level of confidence on whether there is a bird sound presence. Here are two examples on how the model works. The baseline example here has no clear bird vocalization presence, so as our model suggests, low confidence throughout the clip. While in this clip, you can see the spikes of confidence, which show positive detection of bird vocalization, corresponding to the bird sounds we heard in the audio clip. The model reaches over 90% accuracy on our validation set. It performs equally well on a hidden test set of 36 clips, where it gives correct detection to 34 of them. With the trend model, we immediately create a small tool to mark the presence of birdsong on longer audio files. Yet, there are still a few ideas hovering over our minds. Can the performance of our model be improved by pre-processing the audio clips? If we want to adapt the model to detecting various other sounds in the future, what can we do to make labeling an easier process? These ideas naturally lead us to explore digital signal processing techniques, with filtering and scaling being the most promising routes to future improvements.
Digital signal processing, DSP for short, is a huge, wide-ranging field spanning decades of research. There exist many techniques that we could have considered as potential candidates for improving or trying to improve the ML pipeline that we'd built. We settled on a few techniques, one of which is known as filtering. When filtering an audio signal, the goal is to attenuate or lessen some frequencies without affecting others, thereby changing what can be heard in the signal. A great way to visualize the effects of the process is by looking at the signal's spectrograms. Spectrograms graph frequency on the vertical axis, time on the horizontal axis, and the amplitude of the frequency using a logarithmic scale represented by the color. If you look at these two spectrograms of the same audio signal before and after filtering, you can see that around 5500 Hz, the frequencies are much weaker on the right than they were on the left, which makes this sound like
The other main technique of focus is scaling. More specifically, we delve into time scaling and pitch scaling to aid our progress. We mentioned earlier that we have over 1700 hours of audio data, which is far too much to manually process. But what if we can cut that down to half the length, or even a third of the original length, while still preserving the original pitch? This technique is known as time scaling, where we can stretch or compress the audio clip duration with some specified factor. Cutting down on audio duration means researchers can more efficiently label the data. In turn, this can potentially drive the identification accuracy up. These two spectrograms show an input audio clip and its time-scaled version, where the duration is half as long. We can clearly hear the effects of this method. Since the AudioMoth records within the ultrasonic range, there can be lots of vocalizations such as bat calls that we simply cannot hear. Similar to time scaling, What if instead of scaling the duration of a clip, we can scale the pitch of a clip? Pitch scaling allows us to do just this. Pictured here are the input and output spectrograms, where the output has brought the ultrasonic frequencies at 25 kHz down into the human hearing range. We can hear a new vocalization that we have not heard before. This is our ultrasonic vocalization.
Eventually, we determined that some of the DSP techniques we implemented, especially filtering, were actually confusing the ML model, which caused it to produce inaccurate and misleading results. Although ineffective for their original purpose, the library we've built out of these DSP tools can still process audio so that humans can listen and obtain meaningful data from it. Thanks for watching. We're the Automated Acoustic Species Identification team, and we hope you enjoyed this video.